All right, so we've been working with the unit circle, and we've been talking about points around the unit circle. And just to remind you, for whatever reason, we start right here at the point 1 comma 0, and we rotate around the unit circle counterclockwise. And this can be a useful thing when you're trying to imagine something that is spinning around, like a Ferris wheel or a merry-go-round. It's also useful in other situations, like if you're trying to think about a planet orbiting, or other situations where things just happen to kind of go up and down periodically, like maybe a tide or anything that is swinging back and forth. But what I want you to think about is a question of how can we tell if a point is on the circle? So there's a couple points that are easy to find on the unit circle. I just labeled 1 comma 0. Up here, 0 comma 1. Over here, negative 1 comma 0. And these are pretty easy to find because the word unit circle just means the distance from the middle, the distance from the origin, is 1. And so if you go east, south, north, west, it's pretty easy to think, okay, it's just one step away, so it's going to be some combination of 1 and a 0. And now you might be led astray here and think, oh, a point is on the unit circle if its x and y values add up to 1. That's not a reasonable idea. But I can show you really quickly that's not true. This point right here is the point 0.5 comma 0.5, definitely not on the unit circle. So it's not enough to have the x and the y values add up to 1. As we can see with an example right there, it definitely doesn't work. And our other example over here, negative 1 comma 0, that doesn't add up to 1 either. That adds up to negative 1. So it's kind of confusing because our x and y values seem to add up to different things depending on where you are around the circle. So let's get rid of this 0.5 comma 0.5 point. Well, when I'm looking at my grid lines here, I zoomed in, and so there's a couple points that I can see that are directly on the circle. I can tell this point right here lines up, and I can tell this point right here lines up. This first one is 0.8 comma 0.6. The circle lines exactly up with the grid lines. And again, 0.6 comma 0.8. And that's kind of weird because those add up to be more than 1. If I use symmetry, I can find the buddy points over here. So this is like a buddy point of negative 0.6 comma 0.8. There's a buddy point here of negative 0.8 comma 0.6. And then there's this corresponding points on the bottom as well. What I want to do is, and really this is the key idea for this whole unit, is that every point in a circle can be thought of as part of a triangle. So let's take this point right here and let's draw the triangle. So 0.6 comma 0.8, if I draw a triangle that touches that point like this, then I should have some familiar tools come into mind. This is not just any triangle, it's a nice right triangle. And the x-coordinate of 0.6 is the length, the width, I guess I could say, of my triangle, the width. And the 0.8, the y-coordinate, is the height of my triangle. And the hypotenuse, we know the hypotenuse because the distance from the middle to the circle is always the same. And we're talking about unit circle. So we're talking about the number 1. And you can check for yourself that, okay, when I have a right triangle, I know that a squared plus b squared has to equal c squared. So let's just check, does that really work out? Because it's always possible that maybe I was just looking at the graph and it just appeared that 0.6 comma 0.8 was on the graph. Maybe I read the graph wrong. So we're checking, does 0.6 squared plus 0.8 squared really equal 1? Well, 6 times 6 is 36. 8 times 8 is 64. Check it for yourself. 36 plus 64 makes 100. So 0.36 plus 0.64 makes 1. And so I know that this really is a point on the unit circle. I could do the same exact thing for 0.8 comma 0.6, and you would just have the same calculation that I wrote down there. And this explains one of the problems. It also works with our negative values. The beautiful thing about squaring is that if you square a negative number, it also works out to be a positive value. So all of those buddy points also work out to work with the Pythagorean theorem and land on the unit circle. What I'm going to do now is I'm going to choose a point that's not obvious. So let's clear all that writing. Let's say I have a point right here. Maybe I'm curious about this point right here. Ooh, I'm getting some lag. That is a really bad line. That's okay. Let's say I want to get this point. And I am, for some reason, interested in what the coordinates are when I'm 0.2 steps over in the x. I know that this value right here is equal to 1, but I don't know in this situation what the y value is. Geez, the lag is bad. Okay. But I know that I can make a right triangle at any point on a circle. So what I'll do is I'll write down 0.2 squared plus y squared is equal to 1. Let's try that again. Come on, lag. 0.2 squared plus y squared is equal to 1. Well, 0.2 squared is 0.04. This might have to be a give up on the lag video. So you have 0.04 plus y squared equals 1. So I take away 0.04 from both sides. I get y squared is 0.96. So y is the square root of 0.96. And actually, if you think back to earlier, we talked about how if you take a square root, you get a positive and a negative answer. I'll talk about that more in a second. The square root of 0.96 is 0.98-ish. So what we have is y is approximately 0.98. Now, because of the way I drew the triangle, we know that the positive answer is the right one. But the reason it gave me two answers is because there's also this corresponding triangle that I could have drawn down below that also has an x value of 0.2. It just happens to have a negative y value, and that is negative 0.98. So what I've done is I've shown that if you know two coordinates, you can feed them into a squared plus b squared equals 1, or x squared plus y squared equals 1, and that'll tell you if it's on the unit circle. And I've also showed that if you know one of the coordinates, you can use x squared plus y squared equals 1 to get the other coordinate. The last thing I want to do is just remind you that what we're talking about in the unit circle is that if you have a random angle that we have rotated, not a particular angle, theta could be there, or theta could be all the way over here. The x value is the cosine of theta, and the y value is the sine of theta. So the idea that I've been using all along is that x squared plus y squared equals 1 squared, but we can write that in terms of cosine theta and sine theta. And this is nothing to be intimidated about. It's just saying that every point on a circle can be made into a triangle. And if it's a right triangle, we know we can do a squared plus b squared equals c squared. So that means we know that x squared plus y squared equals 1, which can be rephrased as cosine squared plus sine squared equals 1. And the last thing I want to show you is I started this video with a graph out here. And if I click on the equation that I typed in, you'll see it's really just one version of our equation, a squared plus b squared equals c squared. So this is all called Pythagorean identity. because it's just like the Pythagorean theorem, except for it only is with the c value equal to 1. So that's all that is there. And let me know if you have any questions.